All right, well, let's go ahead and get started on chapter 24. And the good news is, this is our very last chapter. The even better news is that it's not long. And that's because after suffering through 234 and the other chapters in 235, you guys know it all. So most everything we're going to talk about, we've already talked about before. There are a few new concepts, but not many. So you actually already know most of this stuff. So it's kind of like a fun time. At the end of class, I will give you quiz 3. Quiz 3 you do from now until next Tuesday, and then hand it in. Tuesday, we will do exam 2 review. And then on Thursday, we have exam 2. Following that, I believe we have a final review. I'm not sure. Might just have a final, but whatever. Final's coming someday. Any questions?
Yeah, question.
Yeah.
Are we going to get a final review guide?
Yeah, probably. Probably. Yeah. I've changed the syllabus so many times, I'm not exactly sure, but probably. Okay? All right, this is an amine here doing gymnastics. Well, this is called pyramidal inversion, and we'll talk about that in just a moment. Amines. Amines are the organic equivalent of ammonia. With ammonia, you have a nitrogen bonded to 3 things, and you have a lone pair of electrons. The chemistry is really all located in the lone pair of electrons. It's an electron donor, and therefore it's a Lewis base. This is amphetamine, very simple structure. It's a substituted benzylamine. This is cocaine. And this guy, this fancy heterocycle, is strychnine. Now, strychnine is really a fairly deadly poison. These are too, but this is even worse. The bottle's even labeled poison. Back in the old days, you could go to the drugstore, CVS, or Walgreens, and you could buy a bottle of strychnine. Well, you can't anymore. Well, sort of you can. These days, however, it's called children's cold calm. Children's cold calm. And the first ingredient on the label is strychnine. Now you might wonder to yourself, how do you get away with this? Well, this turns out to be a homeopathic medicine. And because it's homeopathic, as far as the FDA is concerned, there's nothing in it, just water. But in that water, the first ingredient is strychnine. Nonetheless, it calms you cold nicely if you're a child. Amines. These are some examples. Here we have a nitrogen with 2 methyls. Obviously, this is dimethylamine, trimethylamine, and tetramethyl ammonium chloride. Here we have a chain and a couple things on our nitrogen. We show those using N to indicate the nitrogen substitution. So this is NN, dimethyl propylamide, 3-carbon chain. We'll talk about nomenclature in just a minute. This is benzylamine. We're all familiar with the benzyl group. This is also called phenylmethylamine. When we talk about amines, we talk about their substitution patterns, depending upon how many groups are attached to the nitrogen. Here we have two. This is a secondary, this is a tertiary, and this is a quaternary. Again, another tertiary amine. Benzylamine is an example of a primary amine. Only one group attached to the nitrogen. When we do nomenclature, we're going to use either amine or amino. We're going to follow the basic rules that we always have. We would like to give the amino group the lowest number at the first point of difference. And this is where the amino group differs from some of the things we've talked about recently. It's more like a halogen substituent. The first point of difference is more important than the substituent itself. So let's look at some examples. Here we have three very simple aliphatic amines. These are all primary amines. As we look at this, if we try to find our longest chain containing the amino group, it's going to be this guy, 1, 2, 3, 4, 5, so it's a pent. We want to give the nitrogen the lowest number at the first point of difference. So here we're going to let this carbon be carbon number 1. So we have a pentanamine with a methyl group here in carbon 3. 3-methyl pentanamine. We could also call it 1-amino 3-methyl pentane. Both of those are fully acceptable IUPAC names. Our next guy, the longest chain containing the amino group. Well, it's going to be this guy here. And it's got 1, 2, 3, 4, 5, 6 carbons. Now this one wasn't supposed to pop up yet, but we're going to let that be carbon number 1 because the amino group is in a tie with the methyl group. And the amino group wins on a tie. So this is going to be a 2-amino. Again, 1, 2, 3, 4, 5, 6. So it's a hexanamine. And it's got a methyl group here in carbon 5. 5-methyl, 2-hexanamine, or 2-amino 5-methyl hexane. Both are fully acceptable. Now where things are a little strange with the amino group, but it's the same as if the amino was a chlorine. In this compound, our longest chain is going to be this guy, right? So again, it looks like this, 1, 2, 3, 4, 5, 6. So it's a hexanamine, once again. But if we let this be carbon 1, our numbering sequence would be 2, 4, 5. If we let this be carbon 1, our sequence would be 2, 3, 5. 2, 3 beats out 2, 4. So this is carbon 1. There it goes. So it's a hexanamine with methyl groups at carbons 2 and 3. Again, this is not carbon 1 because you go for the lowest difference. The first difference when you're breaking the tie. So, you know, if this was a chlorine, it would be the same thing. Just think about that. Any questions? Yeah?
Can we call it 2,3-dimethyl? Can we switch it to, or no? Not on this one.
No, the amino has to come first alphabetically. So 2,3-dimethyl-5-amino would be backwards. But make sure it's not 2-amino, because again, 2,3,5 loses out or wins over 2,4,5. That's the point of that one. Let's just look at some simple examples here. Our first one is a cyclohexane. It's going to have 2 amino groups on it. They are 1, 3 relative to each other. And their stereochemistry is, what is it? Are the 2 groups cis or trans? They are both equatorial. Think about your ring plane. They're both on the same side of the ring plane, aren't they? So they're cis. So it's a cis 1,3 diamino hexane. Huh, I got it right. Any question? We want the amino group to be on the parent. So we're going to let our chain be this guy. This would be at carbon 1, so that's going to win. So let's let that be our main chain. And let this be carbon 1. So it's a 1, 2, 3, 4, 5. So it's a pentanamine. Pentane, amine, pentanamine. And in carbon number 4, what do we have? A phenyl group. 4-phenyl, 1-amino pentanamine, or 4-phenyl pentanamine, or 4-phenyl 1-amino pentane. By this time, I hope you've realized that the whole point of nomenclature isn't just to drive you nuts, but it's to be able to communicate. And it really doesn't matter what you call it, as long as the name is absolutely unambiguous. If you're describing this in the chemical literature, it has to be unambiguous. So both of these are unambiguous names. If you introduce any ambiguity, that's wrong. Our last guy. This is always a bit of a challenge. Remember way back when you did, cycloalkanes. The rule was anytime you saw 2 things on the same carbon, that was automatically going to be carbon 1. Well, we've looked at other functional groups, and that kind of went by the wayside. But, again, think of this as a halogen. If it was a halogen, this would still be carbon 1. And it is. So we're dealing with a 1,1-dimethyl cyclohexane with an amino group in carbon 4. Always think of it, an amino group, simply as a halogen, as far as naming goes. So this is 4-amino, 1,1-dimethyl cyclohexane. Any questions? Now we all remember from general chemistry that this nitrogen has 4 things around it. 4 real substituents and a pair of electrons. So the steric number here is 4. That means that nitrogen is going to be tetrahedral. if we look at an amino compound, the fact that this nitrogen is tetrahedral means that this would kind of look like this. Again, it's tetrahedral. The fourth position is our electron pair that's up here. Now, if you look at this, here we have an ethyl group, a hydrogen and a methyl, and a lone pair. That would be a chiral center, wouldn't it? 4 different things around the central atom. However, nitrogen undergoes inversion, called pyramidal inversion, and it does it quickly. So here's our lone pair, that's our 4th position, and very, very rapidly at room temperature, this undergoes inversion. So this goes back and forth. Now I'm sure you've thought about this as you see this go, but in one orientation we have R stereochemistry, in the other we have S. Pyramidal inversion. This would be the S stereoisomer. And when we invert, we would have the R stereoisomer. You cannot isolate isomers of nitrogen compounds at room temperature because they invert so quickly, 10 to the 6 times per second. If this was a sulfur, however, you can take a sulfur and put 3 things around it. That gives the sulfur a positive charge. It's called a sulfonyl ion. And it also has a lone pair, so it looks just like this except it's yellow. And the pyramidal inversion around a sulfur is very slow. So you can actually isolate stereoisomers of sulfonium compounds, but not nitrogen. Any questions? Well, nitrogen is both a hydrogen bond acceptor here and a donor here. So when you have amines, they hydrogen bond all over themselves. Because of that, nitrogen compounds, amino compounds, are relatively high boiling for their molecular weight. They're not as good as water, because water we have one more position where we can hydrogen bond, but they're pretty good. They're better than alcohols in terms of hydrogen bonding. This is why it is possible, or suggested to be possible, that amino compounds, ammonia especially, could possibly support life. Because it hydrogen bonds, or they can hydrogen bond very much like water. And that's essential for every process that we know in biochemistry. Now, amino compounds have this lone pair on the nitrogen, right here. And because of that, they are proton acceptors. We can write this as a simple acid dissociation. Here we have ethyl ammonium, water. Ka describes the equilibrium constant to give ethylamine and hydronium. We can remember back in general chemistry, we can write an expression for Ka. Ka is products over reactants. We also remember that since water is a liquid, it doesn't show up in the expression, so we have to get rid of it. For ethylamine, if we look at this equilibrium constant, it's very, very small. Equilibrium constant is about 10 to the minus 11, which means the pKa for this dissociation is about 10.4. That means that this is a very weak acid, and it's actually a fairly strong base. Weak acid, strong base. If we look at substituted amines, ammonia itself is about 9.25. We just looked at ethyl ammonium at 10.6. Anything that stabilizes the positive charge is going to make it a stronger acid. So here we have electron withdrawing groups, and pKa for difluoro ethylamine is about 7.5. Here we have cyano, here's an ester. All of these are fairly strong acids. They're still all above 7, but they're much more acidic than the basic amine. The bottom line here is that amines are basic. Any questions? Now, way back in chapter 5, we talked about, someone talked to you about SN2 reactions. And one of the things that you did were simple amines. Turns out that the unshared electron pair on an amine can be used as a nucleophile. With something like bromomethane, we can attack the methyl group. Bromine will leave, and we would form, in this case, aminomethane and HBr. Way back in 234, chapter 5, you said, okay, this is fine, this works. The problem now that you're in 235 is that once we get to this point, we have methyl ammonium ion, which can rapidly lose its proton in the presence of a base and form methylamine. Methylamine can react with another mole of bromomethane and give us the secondary amine. Now this guy can also lose a proton. When it does, it can form the tertiary amine. And finally, if this loses the proton, you can go all the way to the quaternary ammonium salt. The bottom line is what they told you way back in 234 was naive. This is not a good way to make substituted amines because all of these processes go on at the same time. An actual example. Here we have bromooctane reacting with ammonia. Primary amine is roughly 45%, secondary roughly 43%. By the time you get to the tertiary amine, this is getting crowded. Because it's crowded, the reaction is slow, so we drop down to just a little bit, and the quaternary is even a little bit more. You can actually push it all the way down to the quaternary if you put in a big excess of the alkyl halide. But bottom line, this is still not a good way to make it. What we've learned in lab is that if you had a mixture of even these two, separating them is going to be really tough because they're both amines, they're both going to be extracted by acid, etc., etc. So this is really a tough separation. There's a better way to do it, and that's using an alkyl azide. If you took your bromooctane and reacted it with sodium azide, the N3 anion. N3 anion is a very good nucleophile. It will convert this into the corresponding azide at this carbon. Once you get the azide, you can react it with lithium aluminum hydride. You only do one substitution, 100% to the desired product. The problems with this is an alkyl azide that you just made. Alkyl azides are remarkably explosive. Remarkably explosive. Turns out if you have 8 carbons on the end, it's not so bad. But if you have less, the stuff is really, really bad to work with. It can go off, badly. Plus you're using lithal, so you have an explosive compound and lithium aluminum hydride in ether. Not real fun to play with. So that's the problem here, but the yield, once again, is very good. The way this works, here's our bromooctane. We're simply going to react it with azide anion. Azide will displace the bromine, and we get the explosive alkyl azide. Turns out the more carbons you have, the better off you are. If you get down to 2 or 3 carbons, you really got to look out. It's very, very dangerous. This can be reduced by lithal very smoothly to give you the amino group. Any questions? Now, if you don't want to take your life in your hands when you try to make something like this, you can use a slightly different method. It's called the phthalimide synthesis. Phthalimide, remember back to carboxylic acids. 1,2-benzene carboxylic acid was called phthalic acid. Well, if we make the amide, bridging the two carbonyls, that's called phthalimide. Turns out that this nitrogen is fairly acidic. So if you dump it in something like KOH, you can form this anion very easily. All right, well, this is a good anion. It's a nice nucleophile. If we react this with an alkyl halide, we can stick something, virtually anything, on the nitrogen. Now, what is this? It's an amide, isn't it? Twice. What do we remember about amides? This is the carbonyl chapter. Amides can be hydrolyzed. If we hydrolyze the amide here, we would get the carboxylic acid and the free amine. So we simply dump this into acid, we get phthalic acid, and we now get our amino group. No danger of explosives. And no lethal. Any questions? Well, let's look at an example. This is dopamine. Dopamine is a biologically active compound. It's a diphenol with a simple ethylamino group as a substituent. Let's make this using an azide synthesis. Now the azide synthesis, all you have to remember is that originally the nitrogen was an azide group in. So, quickly, draw the structure of the azide that we reduced with lithium aluminum hydride to make this stuff. You want all the rest of the dopamine molecule, but you simply need an azide group on the end. Again, the conditions, simply lithium aluminum hydride in ether. Now you ask, how do you make the azide? Well, remember, that's just a simple SN2 reaction with an alkyl halide. So up here, draw the structure of the alkyl halide you need to make this azide to make dopamine. In place of the azide group, all you need to do is place a halogen leaving group. I chose a bromine because it's handy. Again, simple reaction with sodium azide, SN2 reaction, then lithyl reduction, and we get the amino group. So that's pathway number 1. Any questions? Let's go ahead and do pathway number 2. Do the same thing here with a phthalimide synthesis. Draw the structure of the phthalimide adduct down here that can be hydrolyzed to give dopamine. Remember that in the phthalimide, the nitrogen was bonded as an amide twice over to phthalic acid, 1,2-benzene dicarboxylate. Bonded twice over. Therefore, all you have to do is lose your nitrogens, put in some carbonyls, and this is your phthalimide adduct. Here's our nitrogen, 2 carbonyls, it's a diamide. Now, once again, simply give me the alkyl halide and the conditions you need to make this phthalimide from the alkyl halide. Remember, you want the phthalimide anion. You can get that from phthalimide itself with base. And you're going to react it with an alkyl halide. So this used to be an N-. This used to have a leaving group. Let's call it a bromine again. N- displaces the bromine, gives us the phthalimide. Acid hydrolysis gives us the primary amine. Note that this only gives us, both of these methods only give us primary amines. Now, when I first put this slide up, I hope that you all looked at this and said, oh yeah, I know how to make that, because you actually do. You know 2 other methods that would make this primary amine from a simple source. You know 2 of them. Talked about them in chapter 20 and 21. What can we reduce with lithium aluminum hydride to give dopamine? Think way back to chapter 20 and 21, 3 chapters ago. Well, remember nitriles? If you reduce the nitrile, what do you get? An amino group, a primary amine. So if we had this particular nitrile, and we simply touched it with a little bit of lithiol, poof, we get our amino group. What other group do we know that we can reduce to make an amino group? Think about it, not a nitrile, but it's the same oxidation level. It's an amide. If we have this amide reduced with lithiol, we can make this. So there are 4 ways that you know now to make dopamine. Isn't that neat? Any questions? Here's a 5th way. We can do what's called a reductive amination. What if we had this aldehyde? If you have that aldehyde, you can react it with ammonia. Now what's that going to give you? It's going to give you an imine, a carbon-nitrogen double bond where the carbonyl used to be. An imine is a very reactive species. If you reduce an imine, you can convert it directly into an amino group. Here's our ammonium intermediate. Again, the nitrogen displaces the oxygen to form the carbon-nitrogen double bond. Rainy nickel. Rainy nickel is just a very porous nickel that's been exposed to hydrogen gas. So it's handy. You can, it's in a bottle. You pull it out. It's got the hydrogen already in there. You dump it in, shake it up, and by gosh, you reduce it, and you get your amino group. Very convenient. Any questions? Reductive amination is also used illicitly to make methylamphetamine. This was a synthetic method of choice. You may have seen it on Breaking Bad. You have phenylacetone here instead of an aldehyde. You dump in ammonia, rainy nickel, and by gosh, you get methylamphetamine. Problem is that you get both stereoisomers. Methylamphetamine is a chiral compound. One stereoisomer makes you nuts, and the other one makes your nose clear. It's a nasal decongestant, very effective. So you wind up with this mixture of stuff that makes you nuts and not congested. Most people try to separate the stereoisomers. That is difficult to do. But for a long time, that was the preferred way to make illegal methamphetamine. Any questions? It's a whole lot less dangerous than doing what they did on Breaking Bad. All right, say we have an amino group here, and we have something like acetyl chloride. We already know what's going to happen based on chapter 22. The nitrogen is a nucleophile. It's going to attack the carbonyl, and we're going to get a tetrahedral intermediate. When we do, that tetrahedral intermediate can partition. So the attack step Simply looks like this. We lose the chlorine from our tetrahedral intermediate, and here we've made a simple amide. We can do the same sort of reaction. Instead of using an acid halide, we use a sulfonyl halide. Now, a sulfonyl halide has a sulfur and a couple extra oxygen, and you kind of get confused by all those things, but it's the same chemistry. We're going to attack the sulfur. We actually form a pentavalent sulfur intermediate instead of a tetrahedral intermediate. That breaks down with expulsion of the chlorine, and we make a sulfonamide. Sulfonamides are actually a very interesting class of compounds. If you ever have taken antibiotics, you may have heard sulfa drugs. The very, very first real antibiotic that was ever developed was a sulfonamide. It's this guy, this stuff, whatever that is, however you say that word. This was developed in the 30s in Germany, and it was actually the very first antibiotic that really worked. Now, phenol was still the standard at this time. Remember, phenol was carbolic acid, really nasty stuff, but it did kill bugs. This killed bugs, but did not kill the host, which was even better. Sulfonamides also have a place in qualitative organic chemistry. And this is something that's important to remember if you ever take a standardized test, called the Hinsberg test. Let's say that we had an amino group. We know it's an amine, and we react it with toluene sulfonyl chloride to make the sulfonamide. Well, turns out that this nitrogen is fairly acidic, just like phthalimide was acidic. So if we take this and we dump it in good, strong base, we're gonna hit, this is the sulfonyl part, we're going to lose our proton here and form the anion. Now the anion, and with this potassium, is a salt, and it's soluble in water. So let's pretend that you had a compound that you had identified as being an amine, and you wanted to know if it was a primary, secondary, or tertiary amine. If it was a primary amine, when you made the sulfonamide, dumped in base, it would go in solution. Base soluble, primary amine. If, however, we had a secondary amine, there's no hydrogen. So it forms a sulfonamide, but does not dissolve. Just sits in the bottom of your tube as a little wad. If you had a tertiary amine to start with, it has no hydrogens to react with the sulfonyl chloride, and we don't get a sulfonamide at all. The thing to remember, this is called the Hinsberg test. Again, this is an important question. It shows up on multiple choice exams. Primary amines dissolve, secondaries don't, tertiaries don't react at all. Any questions? I remember we talked about simple SN2 substitutions on amines. There's a process called exhaustive methylation. Let's pretend that we have a simple primary amine. Here we are with our friend dopamine again. If we put in a ton, literally a ton, of bromomethane, we will alkylate to make the primary, then the secondary, then the tertiary, then the quaternary ammonium salt. We do that, we wind up with this guy. Now, this is a decent leaving group. The trimethylamine with its electrons are all set up to go. All we need to do is have something to pull off the proton from this carbon. We can do that by treatment with silver oxide of all things. So if we take our quaternary ammonium salt here, treat it with silver oxide, it's a good strong base. What happens is the base will pull off this proton, it's an E2 elimination, and we wind up with the alkene. So it's a nice simple way, Hofmann elimination, to convert amino groups into alkenes. We lose the amino group and wind up with a double bond. Once again, you need silver oxide as your base in order to do this. Plain old KOH or tert-butoxide doesn't work. But there's a unique thing about the Hofmann elimination. Remember, the standard rule for E2 elimination, Syseff's rule, what are we going to form? The most highly substituted alkene. Unless you're doing a Hofmann. Then you form the least highly substituted alkene. So if we had this compound and we wanted to do, or wanted to form this guy, we would use tert-butoxide, convert the amino group into a different leaving group, and we could form the Sysef product. If instead you wanted the anti-Sysef product, you would simply do the Hofmann elimination. The choices in organic chemistry are just amazing. Any questions? Well, Hofmann didn't just do this, he did other things. One of the things that he did was to look at a rearrangement. Strange thing. Hofmann found that if you took a simple amide, you treated it with base and bromide in water, that by George, you would lose the carbonyl of CO2 and you wound up with the primary amine. Kind of magic, really. Can't imagine how in the world they came up with these conditions, but some student working in the dungeon somewhere did it and went up to Hofmann and said, "Hey, look what I found." And he called it his rearrangement. It's a very neat way to take an amide, convert it to the amine. And it worked nicely. Think about, you have an amide here that could come from a carboxylic acid, make the acid halide, make the amide, and then you make the amine directly. So it's a nice versatile way to do these things. The other one is much more dangerous, called the Curitus rearrangement. Let's pretend that we had an acyl halide here, so chlorine or bromine or something. If you react that with azide, you make the acyl azide. Okay? Now the acyl azide, if you heat it up and you live through it, will give you CO2, nitrogen gas, and the corresponding amine. Acyl azides are remarkably explosive. Remarkably explosive. You know, this is N3. It really wants to be nitrogen, doesn't it? Here you don't have a whole lot of carbons and oxygens attached to it, and you've got to heat it up. I actually have experience with this in graduate school. There was a guy that was trying to make a penicillin, actually. And it involved synthesis with an acyl azide. Made the stuff, it was fine. It was sitting in an NMR tube. Now, we don't know what that is, but an NMR tube is about 5 millimeters around. It's a little thin tube, and you put your sample in there to do an NMR. So we had made this acyl azide. It was dissolved in deuteral chloroform, just sitting on his desk, and he was there talking to me, just talking, and then suddenly it went, wow! Now, nobody was hurt. The test tube was in the ceiling still, I'm sure. But very dangerous things. Curitus rearrangement works nicely, but really, really dangerous. Any questions? All right, if our benzamide experiment would have worked, and it didn't, we would be familiar with the infrared spectra of amines, amides, things like that. There are bands that are highly characteristic of amines, and they occupy really two regions. Down here in the 3400 region, we get a very nice NH stretch. Once again, this is hydrogen bonded, so it's a little broadened. It's not nearly as broad as an alcohol, but it's a fairly broad peak. Again, this is the NH stretching. With an amine, you also get NH bending. So you have your nitrogen, you have hydrogen. It doesn't just stretch up and down. It can wag back and forth. That's a very significant band, and it tends to show up here about 1600, the NH band. With an amide, you get two of them. They refer to them as amide 1 and 2. Biologists do, I don't. But it's simply an NH band. Any questions? Well, we haven't done this in a little while. So let's just look at a spectrum or two or three and see if we can identify a compound. Now, clearly it's going to be an amine. We look at our formula here, we have a nitrogen in there. Remember when we do degrees of unsaturation, we have to subtract an NH from our analysis. So if we look at this formula, it's the same as C7H8, which gives us 4 degrees of unsaturation. Now remember, whenever we see 4 degrees of unsaturation, it kind of screams at us that we're dealing with an aromatic compound. We look at our spectrum here. Our molecular ion is 107, and we lose 1. Okay, I have no idea. But we lose 1. Look here at 91. We actually have a little peak here, don't we? And we have something at 77. That's all consistent with, benzene rings, maybe a benzyl group, but it's not a simple benzyl, because otherwise 91 would be really big. So let's leave it at that. Let's look at the infrared. This is the same one we just looked at, but let's look at all the rest of it. Down here at 3400, we clearly have an NH stretch. Here, this is on the high side of 3000. So this is probably consistent with an arene CH stretch. We have a little peak here on the low side of 3000, which kind of suggests we have sp cubed CH as well. Now we don't have any triple bonds. We don't have a carbonyl, but we do have nice bands here for NH bend and our benzene ring at about 1600. So based on this, it looks like an aryl amine of some sort. Benzene ring and an amino group. That's what we know so far. Any questions? Our NMR looks like this. Proton NMR, well, down here at 7.2-ish, have a nice peak, a little bit of splitting up, worth 5 hydrogens. That's a monosubstituted benzene, isn't it? Monosubstituted benzene, 5 hydrogens. And we have 2 singlets here. If you add it up and subtract our 5 hydrogens, we have 2 and 2. One is probably a CH2, and if this is an amine, the other one would be a CH2. I'm sorry, NH2. Probably this guy would be the NH2 because nitrogen is more electronegative. So here we have 2 singlets down here. One CH2 is an electronegative environment, possibly the amino group. This is consistent with a monosubbenzene, and this is probably a garden variety CH2. Our C13. Look at our pattern. Singlet, doublet, doublet, doublet. That's what you see for a monosubbenzene, isn't it? And finally, what's left over, we have a triplet. That's a simple, mundane CH2. So putting it together, we have a benzene ring, monosubstituted. We have a CH2 and an NH2. This is simply benzyl amine. Now, the one thing that I hope is going through your mind is, if this is really benzylamine, why didn't we see a better 91? Because with an amino group, the primary cleavage is always loss of a proton to get the imine. That's the M-1. Once we do that, the next peak, next predominant peak, is cleavage of this to give our 77. So the benzyl group doesn't show up because the predominant cleavage is loss of a single hydrogen. Any questions? On the final exam, you will see one more of these integrated spectroscopy problems. If you have to take the final. I hope you don't. I'm sure you do too. Any questions? All right, let's just review some very simple reactions. Go ahead and quickly write the products for these simple reactions. Our first one, our nitrogen is simply acting as a nucleophile with an alkyl halide of some sort. Simple SN2 reaction, we're simply going to substitute at least once to give us the primary. We also realize we can get the secondary and even the tertiary amine as our product. Our second one goes back to chapter 22, 23. We're doing acyl transfer. We have acid halide, or we have an ester, or an acid anhydride. All going to react the same way. Leaving group is different. Halogen here, OR here, alkylate here. Nonetheless, we make the corresponding anode. Simple acyl transfer reaction. Remember, when you're looking at an acyl transfer, you want to look at the tetrahedral intermediate, decide which leaving group, pay attention, is the strongest acid. That's the one that will leave. The conjugate acid of the leaving groups, I'm not home, will give you the leaving group for this. If we take an amino group, react it with a carbonyl, so this is a ketone raldehyde, and then we reduce. We could reduce with chlorhydride, we could use grainy nickel. This is a reductive amination, isn't it? This is how you make methamphetamine. Carbonyl, ammonia, reduction, we simply make the amino. And finally, this is para-toluene sulfonyl chloride. We know the nitrogen is going to attack, chlorine is going to leave, and we will make the sulfonamide. It's a primary sulfonamide, so it is base soluble. Let me communicate with my son while you work on these two. Once again, we have simply an amino group. This is a secondary amine, however. And now we have a carbonyl. If these two were to add together, they would form, by definition, a nitrogen with a double bond to the carbon and a positive charge. That's an ammonium ion. Because of that, it's unstable. This will lose a proton from one of the groups and form an enamine. Enamines, we remember, are useful because the electrons go back in, show up on this carbon, and they can be used as a nucleophile. And finally, Mr. Hofmann in his elimination. We have a quaternary ammonium salt. We have silver oxide. We will get an E2 elimination to give the alkene. more. Here we have phthalimide. Going to treat it with base to make the phthalimide anion. Going to react it with an alkyl halide. And then we're going to hydrolyze, either acid or base. So we're going to hydrolyze off the imide group and wind up with the primary amine. The simple phthalimide synthesis. Sodium azide. React with an alkyl halide. Make sure you got a big chain here. Otherwise, it's going to blow up in your face. Take that, reduce it with lithal. We simply convert this to the primary amine. And finally, as we said earlier, a nitrile with lithal does the same thing as an amide with lithal. We're going to simply reduce the carbon-nitrogen triple bond and form our primary amine. Any questions? Well, let's move on to Aryl amines. Now, when we talked about aromatic compounds in general, we addressed Aryl amines. This is aniline, benzene ring with an NH2, beautiful compound. Aryl amines really were the start of organic chemistry. This is where it all really took off, because this monetized organic chemistry. Back in the old days, if you wanted something dyed, you had to use, I don't know, indigo or something from a plant or tomato or whatever. But Perkin took home a bunch of chemicals he shouldn't have, worked in his basement he shouldn't have, and he discovered that if you took aniline and did some strange things to it, you could make 3-amino 2,8-dimethyl 5-phenyl 7-phenylamino 5 whatever chloride. This stuff. This doesn't sound very neat, but this is mauve. It was a beautiful purple color, could totally replace indigo. It was stable, and you could make it in the bench. And it made him extremely wealthy. Everybody was trying to get aniline, which is the source of this stuff, and it was really the start of industrial organic chemistry. Another one that he developed, this guy, mellow yellow. Again, with all of these compounds, they were stable. They took to cotton like mad, made a very stable dye, and you could replace all of the natural dyes. Lots and lots of money came from this. Aryl amines. We speak of aryl amines, we're really talking about aniline. Aniline is the parent. When you name these things, aniline is an acceptable parent for a UPAC. So this would be 4-bromoaniline, 4-bromo-3-chloroaniline. The nitrogen gets carbon number 1, even though it's not the lowest order. We can have substituents on our nitrogen. When we have substituents on the nitrogen, we indicate it with an N. So this is N-methyl aniline. 2 of them, NN-dimethyl aniline. And this is NNN trimethyl aniline chloride. So, when you're naming amines and you have substituents on your nitrogen, you simply show them using the N and then whatever the substituent happens to be. Any questions? Now, the chemistry of aniline is really not much different than the chemistry of other amines. It has a lone pair of electrons, and that's where all the reactivity is. But it does one very unique thing. If you take aniline and you react it with nitrous acid in a strong acid solution, you get what's called a diazonium salt. Now, this is all done in solution, so you never isolate this stuff. Clearly, as you look at this nitrogen wants to leave, doesn't it? So this is an extremely reactive compound. This is HNO2, not 3, nitrous acid, and again, a diazonium salt is what it's called. Because this is such a great leaving group, it has its own set of reactions. These are called collectively the Sandmeyer reactions. If you take a diazonium salt, this is H3PO2, that's not a typo. This is phosphorus acid. With phosphorus acid, a diazonium salt, the nitrogen will leave, substitute a hydrogen, and in this case we would simply make benzene. Now this is really useful synthetically because if we have a nitrogen on a ring somewhere, we can use it to direct substitution, make a compound, then make a diazonium salt, and get rid of the nitrogen. Kind of a neat reaction. If you take copper 1 chloride in the presence of HCl, you can displace this and actually replace the diazonium with a halogen. That's kind of neat. You can do the same thing with bromine. Again, copper 1 bromide, HBr. We get bromobenzene. And finally, iodine is so reactive, you don't even need the copper. This can displace it directly and give us the corresponding iodide. Iodide especially is hard to make, so this is a neat way to make it. Think about it, once you get these guys, you can convert them into Grignard reagents, and they do darn near anything with them. So the versatility is really phenomenal. Again, collectively, these are the Sandmeyer reactions. Sandmeyer was the guy. We can also do an interesting thing with cyanide. Cyanide in the presence of copper 1 cyanide. Once again, we can substitute the CN and make this guy. Now this is really, really interesting. We've added a carbon. We know we can reduce this to an amino group. We can hydrolyze it to a carboxylic acid. We can do just lots of stuff with it. Very, very useful. Now, water and acid. We know that in order to go to benzene that we needed phosphorus acid. But if you just boil it up in acidic solution by itself, you go to phenol. Nice way to convert something with a nitrogen here into a phenol. Now, if you react it with phenol or an aryl amine, you get a very, very interesting reaction. With these guys, we get what's called a coupling. Phenol, due to resonance, has electron density at the ortho and para positions. The para position will attack the diazonium salt, and we make this coupling product. This is how we made the yellow stuff, mellow yellow. Same thing if we have an amino group. So here's the substitute of aniline. Again, electron density at the para position. And we make, this is our methyl yellow compound directly. Very simple, very interesting chemistry. It works very nicely. Let's just take a second to make sure we understand exactly how this is happening. Remember with phenol, we can move the electrons in to the ortho and para positions. So we wind up with this resonance form, electron density here. Move these guys in, electron density in the para position, and once again in the ortho. Coupling seems to only occur at the para position, probably because of steric effects, and that gives us our desired coupling product. So here's our electron density. It attracts or attacks the diazonium salt, and we make our double bond. Called a coupling reaction. Very, very useful. Very interesting. Any questions? All right. Oh, here's our stuff. Kind of a funny way to draw. Oh, I drew it this way because remember here, this is an sp3 carbon. In order to restore aromaticity, we simply have to lose the hydrogen, just like electrophilic aromatic substitution. And boom, we're at our coupling product. All right. Why don't you quickly give me a synthesis of 4-bromo-aniline, starting with aniline. Now, hopefully what's going through your mind is the amino group really activates the ring, doesn't it? Electrons are going to be pushed ortho and para. So we're going to do ortho-para substitution. Typically, we might say, okay, I'll take bromine and iron 3 bromide and make it. That would probably work. But actually, aniline is so active that if you did this, you would actually wind up with tribromoaniline. You don't even need the iron 3 bromide. It is so reactive that you cannot stop the reaction at the monobromination stage. So this pathway will not give you the monobromo product. Now, as a young organic chemist, I'm sure that leaves you frustrated. And you're wondering, how in the world would I do this? Well, what you have to do is temper the amino group here. Make it so it's still orthopara directing, but it doesn't go nuts. To do that, you want to react it with something like an acid halide. And that would give us How about that? Benzamide. That's the one that didn't work for us, right? Now, this group is also orthoparadirecting, but it's got the carbonyl here that's also pulling on the electrons. So because of that, it is orthoparadirecting, but it's not nuts about it the way aniline is by itself. So if you simply take this stuff and you do the bromination, you will very cleanly wind up with the 4-bromo acetamide. Once you have the 4-bromo acetamide, if you want to get back to 4-bromo aniline, all you have to do is hydrolyze off this group with a little bit of acid or base. So bottom line here, if you want to do nucleophilic or electrophilic aromatic substitution on a ring containing an amino group, what you have to do is temper it by converting it to the amide, do your substitution, and then hydrolyze it off. Any questions? Yes?
On the BR2, why do we have 3 BRs on the final product?
Because this is an excess of bromine. So as soon as the first one hits, the second 2 hit, boom, boom. It's impossible to stop it at the monobromo product. Same thing with phenol. If you try to do this with phenol, you always wind up with the tribromo phenol. Yeah.
Is there a second step missing on the last one?
I'm sorry?
Is there a second step missing on the last one?
Yeah, here you just have to hydrolyze this off to get to the monobromo aniline. See? So here we have the acetamide. Simply dump this into acid, lose this acid or base, either one, lose the amide group, and we make our product, the 4-bromo amide. You'd also get some too, but mostly it would be the 4-bromo product. Any questions? Well, you know, by George, we made it.